we were talking about linear program. We know what is a linear program. What did we discuss last class? We were talking about solving or understanding the solutions to linear programs, and then we started the simplex method. What is the first thing we discussed? One of the things we discussed was local minimum equals global minimum for LP, right? Because it's a class of convex optimization problem, so that way it's nice. Okay. And where do the solutions to a linear program occur? Well, in linear programs, you're essentially searching over a polyhedron, right? Right. The solutions occur always at a vertex or a set of vertices. Okay. And how do we identify? So if this polygon is represented by V, how do we identify the vertices? Well, M plus N. We are searching in Rn because X belongs to Rn. What do these represent? These represent M inequalities, right? There are M inequalities that describe the region inside the polygon along with the boundaries. But what defines a vertex? Yeah. Well, in R2, yes, intersection of two half planes, but in general, how many constraints have to be active here in general? Well, in R2, there are two constraints need to be active. In general, if there are N constraints, then we have, and this is geometric picture. What about algebra? Algebraically, what do the vertices correspond to? Yes. Okay. And how do we identify basic solutions from in the standard form? What is the condition? Wait, how do we get the basic solutions from here? Right. So this is the equality sign. That means these constraints are always active. So we choose M columns and then solve for X equals B. So the corresponding Xi's would be some non-zero value. And then we set the rest of them here to be equal to 0. And those together form a basic solution. Okay. And when is a basic solution a basic feasible solution? Right, when all all the non-zero elements of a basic solution are positive. If any one of them is negative, it's a basic solution, but it's not feasible. Okay. What about this? We also talked about degenerate. When does this occur geometrically? Right. More than n constraints are active. And in terms of the basic solution, what would that correspond to? When there are more than, yeah, you're right. What is it? R0. Okay. And then we looked at a specific example, right? All right. Okay. Before that, how do we identify adjacent vertices? Well, each of these vertices, well, this vertex requires these two constraints to be active. So let's say this is A1, A2, A3. This vertex requires A1 and A2 to be the constraints using A1 and A2 to be active, whereas this requires A2 and A3 to be active. Both of them share one common vector A2, so these are adjacent. So whenever you have vertices that differ by only one constraint, then they are adjacent vertices. And what is the idea behind the simplex method? If somebody were to ask you to explain how the simplex method works, what would you say in one sentence? Well, you start because we know the solution occurs at the vertex. You start at one vertex, and you simply jump from one vertex to an adjacent vertex, as long as your C transpose X keeps reducing, because we were talking about minimizing C transpose X. So you continue that till you reach a point where, if you move to any of the possible adjacent vertices, if C transpose X increases, that means you're at a local minimum. That means that's a solution to your problem. Right. We looked at a specific example. You'll have to tell me the equations again. The problem that we were solving. Yeah. What is C? Was it this? Okay. What was what were the okay. So the problem was x1 plus x2 less than 5. What was it? X1 was 3, right? Okay. Okay. This is not in the standard form. When you convert it into the standard form, um, what is the augmented matrix? 1, 0. Okay. And then this is 1, 2, 4. We chose the first set of basis vectors to be A3 and A4. And from this, what is x1 cap? Well, you're solving just this system. That means A3 and A4 have to be, x3 and x4 have to be 5 and 3. And that means you can set the other two to 0. Okay, and what is C tilde? Okay. What is sorry, what? This one? Okay, here. You've chosen these two as the basis. So you essentially now solve for A3, A4, X3, X4. Because you're only using these two to solve for 5 and 3. And the variables corresponding to these two columns are only X3 and X4. This is an identity matrix. That means X3, X4 have to be 5 and 3. So you keep these and you make everything else 0. Everything else is X1 and X2. X1 and X2 are set to 0, X3, X. Okay, this is 0. Okay. And then we found out what is R1, the amount by which we expect C transpose X to reduce. How much was it? Well, you can either use A1 or A2. Those are the only two possibilities. What is this? So we choose this. Okay. So R1 is the lowest. That means column 1 will enter now. Means A1 enter. But we need to find which one we remove. Okay. How do we find that out? Well, we know A1 enters. We take this. We divide each of these by the elements of the column that is to enter, as long as the element is positive. Okay, if it's 0 or negative, we ignore it. So if you divide the two, you get 5 and 3, and you choose the index corresponding to the minimum of that value. That's the second index. Okay, that means A1 will now be the second basis vector. Second basis vector is where the second element is 1. So now we know the second basis vector here. This is the first basis vector, second basis vector. That means A4 leaves. So what leaves is a min of 3. That's the second one. Means L equals to leaves. That means now, so these two were our original basis vectors. Now we come back to the same matrix. See, this enters and this leaves. And we need to make this the second. How do we do that? Well, we can do row-wise operation. If you do that, what do you get? Okay. So now we have this and this. These two together form an identity matrix. So our base is now A3 and 1. Sorry?
Of the A1 and A1 and A2.
Sorry, one of you at a time.
A1.
This forms the identity matrix. Otherwise, it's 0, 1, 1, 0. What is x2 now? If you solve for this, what will you get? 3, 0 is it? Why is it 3? Wait, first 3. Yeah, okay. Okay, that's fine. What is C tilde transfer? Sorry, minus 2, 3. So there is a decrease. So this is all right. Okay, all right. Now tell me what is so the now we can still verify if what happens in the adjacent vertices. So to that, the only adjacent vertices are these two, corresponding to A2 and A4. So what is R2? Tell me what R2 is. C2 is, what is C2? C2 is minus 1. This one. Well, we're talking about A2. So we 1 times the C value corresponding to this column, 3, right? That is 0. So it will be 1 times 0. And then 0 times the second basis vector is A1. A1 is minus 2. So it will be plus 0 times minus 2. This will be minus 1. What about R4? C4 is 0. It will be minus 1 times the value, C value corresponding to this, that's 0. And then 1 times the C value corresponding to this, that's minus 2. So that will be 0 minus 0. This is not good. If you take this, your C transpose X will go up, which is something we don't want. So this is what we choose. So this means what leaves? Well, A2 enters. You simply divide this by this. If it's non-zero, it's positive. So the only thing that we can divide is this. That's the only option. So we choose this. And that corresponds to 1. That means the first basis vector exists. The first basis vector here is A3. So A3 leaves. And now we have 0, 1. So A1 is as it is. A2 enters, A3 leaves. So this. So this will be 1. 3. What is X3 cap now? 3, 2 is it? Yeah. So 3, 2. Is that okay? Okay. What is C transpose? Still lower. So that's good. What about the adjacent? The only adjacent ones are R3 and R4. What is R3? What is R4? A2 what? Yes. No, no. Here. So we are saying solve this system using only columns A1 and A2. Okay? The reason I've written it like this is because then this is the identity matrix. So all I'm saying is solve this A2, A1, but the variable corresponding to A2 and A1 would be X2, X1. If I see, I can write it like this. Okay, then this will be A1, A2, this will be X1, X2. So what you're solving for is this 0, 1, 1, 0, X1, X2 equals 2, 3. If you solve for this, X1 will be again 3, X2 will be. All I've done is I've switched this so that this is the identity matrix. You simply read out what is here as your solution. That's all. Yeah, what are these two? So just tell me the value. What do you get? Yes. Okay. What does it mean? This simply means if you switch to any of the other basis vectors that are available, C transpose X will go up. That means this has got to be a local minimum. That means that is the solution. That means if this is a local minimum, that's also the global minimum. So the solution really is okay. See, this agrees geometrically also. Right. So x1, that's one of them. This is this region. And then you have this. See? So the region that we are looking at is really this. Right? And the polyhedron over which we are searching is this. And what about the contours of C transpose X? What do those look like? What are the vertices though? Let's write down the vertices. This is easy. What about this? No. What are the contours of C transpose X? What will they look like? Well, this is C transpose X. Minus 2x1 minus x2. Yeah, but what is the slope? Everything depends on the slope, right? Because it's one of those contours will exactly touch at one of these vertices. So the slope will really change what is your solution. Here. I mean, just sketch it out, right? What will, for example, substitute 0, minus 1, minus 2, minus 3, and see what do you get. So the easiest thing to do is to make one of the variables 0 and look at what the other variable is, then you can join. Make x1 0, what is x2 for a given equation? X2 0, what is x1? And then simply just join the line. Okay, what is the slope? So what about the line that passes through this point? 3 0, that will correspond to that. The value corresponding to that will be minus 6. Where will it intersect here? It will intersect at 6. Right? So this is 5, let's say this is 6. Okay. What about here? -5, if that was -5, -2x1 minus x2 was 5. I mean, it'll intersect through this point. Where will it intersect here? 2.5, right? Because x2 is 0, -2x1 is -5, so it will be. That means if you move in this direction, it reduces further and further. So the solution really is this. And what does this correspond to? That's that. I mean, you can also visually see the slope is, of course, greater than the slope of this line. So if you move it along, the only place where it can touch is at this point. And that's what we find the solution. Okay. We will just do one more example for you guys to get used to this idea. And say, yeah. Let's say we want minimize. I'll write this down first. X1 plus x2, 5, x3 is equal to 1. Here. And this is minus 2 minus x3. I won't do the steps. You can tell me what the steps are, and then we'll. Shall I remove this? What is the augmented matrix? Zero is it? Does it start with 0? Okay. 1. Okay. 1, 1. No. There are 3 variables, and there are 2 inequalities. That means we need at least 2 more slack variables, right? Free, or what did I call it? Slack variables or dummy variables. That means there have to be 5 columns. Yeah. Okay. Before that, what is the geometry of this problem? It's in 3D. Let's draw it. Okay, this is x1, x2, x3. What is the first constraint correspond to? No, these are not straight lines, no, in 3D. These are planes in 3D. What does it correspond to? Triangle where? X3 does not matter. That means that plane can take on any value of x3. But x1 and x2 are constrained. Sorry. Huh? Rectangular. Sorry, rectangular plane. Is that what you mean? Is it rectangular? Hey, how can it be rectangular? It's a plane, no? For example, if this was equal, what does it correspond to? Okay, it's a plane that cuts through the xy x1 x2 plane here like this, and it's parallel to your x3 axis. Okay? So it's this plane. If that was the only constraint, right, then everything within that cylindrical prism, is that right? Its cross section is a triangle and it's infinitely long. Then that would be the region in which you search. But there is an additional constraint, x3 less than 1. What would that correspond to? What plane would that correspond to? X3 less than or equal to x3 equal to 1. What plane would it correspond? X1 and x2. So essentially what you have is this. This. You're searching inside this. Okay. And what about the contours? Where are those planes? Right? Where would those planes be? Yes, where? Here? Yes. So if you looked at the contours of those planes, and it's see that the planes corresponding to different values of this will be planes that are parallel to x1. Okay, and they will intersect with the x2 x3 plane like this. So you know the solution has to be this vertex. So we'll verify that in fact this comes out to be the solution. Okay. You can simply tell me what B1 you choose first, and then what is x1, and then what do you do next? A2, A3, is it fine? Whatever you like. Okay. What is x1 then? Cannot be 5, 0, right? Because A1 is not here. That means A1 set to 0. So so these two were chosen. You have three other options. What is R1, R4? No? What is R1? Did somebody find R1? What do you get for R1? 1 plus 1. Okay. Okay. Yes. What does it mean? I mean, you've already chosen the optimal solution. What does this vertex correspond to? Well, we know this. This is what is this point? This point? Okay. This one. What is this point? We know then this point, right? That's a solution. I mean, if you had chosen something else, if you had chosen these two, then you'd have found one of these would be negative or some of them will be negative. So you move because you by chance chose this as the first basis. You arrived at, I mean, you started off from the optimal solution. Fine. We'll keep the constraints like this. We'll just make one small change. Instead of this, let's say we're minimizing. Tell me how the problem changes. If you want to choose this as the first basis, that's still okay. How do these change? Or before that, what is C transpose X? In this case, we've done with this. What about this? -6? Yeah. It will be -6 in this case also. If you were minimizing this. C is -1, -1, -1, 0, 0 now. Or C tilde. This will also be. Now tell me what is R1, R4, and R5. Yep. You have the first one? 0 is it? Okay. -1 is it? +1. What do we say when? Now what do we say? Sorry? Ah, okay, all right. This is what we got. Fine. It's got the lowest value, even though it's not negative. Let's switch and then tell me now what will leave if that what enters? A1 enters. What leaves? Fine. A1. Tell me what leaves. A2. Why is it A2? A1 enters. So this will be 5. Yeah, you're right. Fine. So now A1, A3. What is X2 cap? Sorry. Ah, did you do this? You don't know how you're getting 0, is it? What is C1? C1 is -1. So it's this value times the C value corresponding to the first basis vector. That is, this is C2. What is C2? -1. So 1 times -1, 0 times the C value corresponding uh, to the second basis vector, which is the third column. That means again -1, -1 minus -1. Tell me, what is C transpose X2 first? Here, I mean, you don't have to continue. You get the same value. So this means when you see a 0, that means if you see a non-negative list of RIs, that means you're already at the local minimum. If one of them is 0, that means there is another vertex. You can move to that vertex and you will not see change C transpose X. Whereas if you move to these two, you will increase C transpose X. Okay. And what is the solution here? Fine. So that corresponds to this vertex and this. That's essentially these two vertices. Right? It says that in this problem, both of these attain the lowest possible value for C transpose X. And that should make sense, because what set of planes do these correspond to? -x1, -x2, -x3. What do they look like? So those will be planes uh, that will form equilateral triangles uh, when they intersect with the x1, x2, x2, x3, and x3, x1 plane. And in fact, in this case, it's -6. So if you substitute this equals -6 and draw the plane, that plane would be essentially this. And that plane touches along this, not just the vertex, but in fact, in this case, it touches an edge. Okay? That means, is there a unique solution in this case? Well, we know there isn't, because both of these already give you. Are those the only two possibilities? Are there two minimizers to this problem or more? More, right? Here, any point along this line actually touches that plane. So you choose any point along in this line segment, including the ends. All of them are a potential solution to that problem. Okay, so there are infinitely many minimizers here. Okay. In fact, you can enumerate all of them by simply doing this. So you know that these two are solutions. Okay, you take x1 cap, you take x2 cap, okay, and then you multiply this by some number alpha, and you add it to, you multiply x2 by some number 1 minus alpha, and you generate a new number. And the condition is alpha has to be, okay. What this essentially does, if you have 2 points and you change the value of alpha from 0 to 1, and let's say this is x1, this is x2. If alpha is 1, x cap is x1. If alpha is 0, then x cap is x2 cap. And what you get by doing this is essentially this line segment. You get all the points in the line segment joining these two. Okay, and this sort of combining two elements like this is called a convex. It's a special case of a linear combination where your scalars are restricted to be between 0 and 1. And if you have two of them, then one of the scalars is alpha, the other one is 1 minus alpha. Okay. And remember, if you had two vectors in some Rn, and you take the linear combination of these two vectors, what do you get when you do the linear combination of two vectors in Rn? Yeah? No. Okay. If you have one vector and you take the linear combination of the vector, what geometric structure do you get? Straight line passing through the origin. If there are two vectors, you get a complete plane. Okay. When you do convex combinations between two points, you get the line segment joining those 2 points. So the geometric structure that you get when you do convex combinations is just that. So that's exactly what the set of solutions that will give you the minimum value for all of this is the convex combination of these two vertices. Okay. Now let me ask you this. Let's say you had a higher dimensional polygon that had some really complicated shape like this. And if you found that, let me write like this, 3 points actually give you the lowest possible value of C transpose X. A convex combination of all 3 of them will also give you a potential minimizer. If you have 2 points like this, you get a line segment. If you had a third point, then your convex combination would be slightly different. You do alpha 1 x1 cap plus alpha 2 x2 cap plus alpha 3 x3 cap, where alpha 1, alpha 2, alpha 3 are greater than or equal to 0, and alpha 1 plus alpha 2 plus alpha 3 should be equal to 1. Okay. This is just a special case of this. Your scalars are all positive, and the sum of all the scalars has to be 1. Then what will happen is you get everything in between. So, you understand? So if you had 3 potential solutions minimizers, then the face formed by those 3 will all solve this problem. Will be minimizers of that problem. All right. That's all I wanted to say about the simplex method. It's just one more thing we will look at. So the problems that we've looked at so far, they did not have a degenerate solution. Right? That means for each vertex, the number of active constraints were always equal to n, not more. But it turns out for the simplex method that we've discussed so far, if you have a problem where you have a simplex method, there are a couple of things that can happen. First one is you can have vertices or adjacent vertices where your C transpose X does not go down, it's not reduce, even though it's not the minimizer. And you can what is called cycling. And this is a more vexing problem, because if you look at the way we solved it, right? So look at this, right? So we said we are always jumping from one set of vertices to an adjacent set. So if I start here, I look at something that has a lower value than where I am. I jump there, jump here, and I keep jumping till I get to the lowest possible value for C transpose X. If you don't have degenerate solutions, then the simplex method guarantees that no matter where you start, you will arrive at the lowest possible vertex in a finite number of steps. Okay, that's the advantage of the simplex method. But if you do have this degenerate condition, it turns out that you can start from a vertex, go about a series of vertices, and then come back to the same vertex. Okay, which essentially leads to you not getting anywhere. Okay, that is again because when you have degenerate solutions, the method that we are following does not always guarantee that you go to a vertex that always brings the value C transpose X down. Okay. So there are of course ways to address this, but the bare minimum version of the simplex method that we've looked at does not address this. So if you have a degenerate solution, then you can get into trouble. Okay, I could not find a simple example for where cycling can occur. This occurs when your dimension is fairly big and there are lots of vertices, and then you can get into trouble. If I come across one, I will let you guys know. Okay, all right. So that's all I wanted to say about about linear programming. So what we will do tomorrow is we'll do a few examples where we would look at a descriptive problem and then see how that problem can be posed in a linear programming form or in the form of a linear program. We won't solve it. We'll only look at how do we pose problems in the form of a linear program. And then we look at some examples from radiation therapy, diet optimization and all that. Okay. Are there any questions so far? Maybe I'll leave you guys with the problem. Maybe try and solve this today so that this method, at least you get used to this method. So let's do this. So think of this as some sort of a temporary Homer problem. Or let me just draw the geometry and you can formulate the algebraic version of it. Okay. And this is okay. And then this is where you're searching. And then what you're trying to minimize is this. You can tell me what is the solution tomorrow. Okay, all right. That's all. Then we'll meet tomorrow.